Hello students, I hope you're having a wonderful day. Today I would like to complete the practice problem with you. It's titled, What Planet Number 2? So what we're going to do is calculate some values based on the information that's given to us. We're going to look up some information in our textbook on page 915 to determine the planet that we need to identify. So let's go ahead and get started. I'm going to read the problem to you, and then we're going to draw a simple picture and start calculating our values. So the problem asks us, a planet orbits the sun at an average orbital radius of 7.78 times 10 to the 8th kilometers. In part A, it wants us to calculate the orbital time period in seconds, days, and years. So let's go ahead and do one of these at a time. What I want to do is draw a simple picture. So we have the sun, and we know according to Kepler's first law that the planets are going to orbit the sun in an elliptical path, with the sun being located at one focus of the ellipse. Okay, so we've got something that looks something like that. So orbital time period in seconds, days, and years. So we're going to use the base equation for orbital time period. It's equal to 2 pi times the square root of the average orbital radius cubed divided by the product of the universal gravitational constant and the mass of the sun. So what we can do is go ahead and plug some values into this equation. So we've got 2 pi times the square root. So remember, the average orbital radius here is the center-to-center distance. So from the center of the sun to the center of this unknown planet. Okay? And we're going to identify this as our sub-planet. This is the average orbital radius of the planet. Okay? That's given to us here, 7.78 times 10 to the 8th kilometers. But we need to remember that the units are in meters when we plug it into the equation. So what we have is 7.78 times 10, and we know that there are 1,000 meters in every kilometer. So if we were to perform some dimensional analysis, we would multiply this by a ratio that would eliminate the units of kilometers. So we would say 1,000 meters divided by 1 kilometer. The units of kilometers would cancel, and then this would become 7.78 times 10 to the 11th meters. So we have to have the units in meters, so we're going to use this value in the numerator here under the radical. So 7.78 times 10 to the 11th meters. And remember that we have to cube this value according to this equation. So in the denominator, what we have is the product of the universal gravitational constant, which is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. We're going to multiply this by the mass of the sun. We know that that is 1.99 times 10 to the 30th kilograms. Okay, so what let's do is let's take out our calculator, and what I want to do is first resolve the values underneath the radical. Okay, so I'm going to start right over here. So orbital time period for the planet is 2 pi. In my numerator here, I'm going to get 4.709 times 10 to the 35th. And remember, we are cubing our numerical value and our unit value. So we're going to have units of meters cubed. In our denominator, this is going to be the product of the universal gravitational constant and the mass of the sun. And this is going to give me 1.32 733 times 10 to the 20th power. Now what let's do is take a look at the units in the denominator. What I first want to do is expand the unit of a Newton. And you know a Newton is actually a kilogram meter per second squared. We're going to multiply this by units of meters squared. So in my numerator right here, I have kilogram meters per second squared times meters squared. And algebraically, we can write this as meters squared over 1. We're going to divide this by kilograms squared. And we're multiplying this by units of kilograms. So kilograms over 1. The first thing that we can do is cancel out one of our kilograms. Okay, so you know a kilogram squared is kilograms times kilograms. Okay, one of these kilograms will cancel. Okay, so it's like this kilogram canceling with this kilogram. So we have 1 kilogram left. So I have kilogram meters per second squared times meters squared in my numerator. This kilogram will cancel. Okay, so now all we're left with is meters per second squared times meters squared. And this is going to give me meters cubed per second squared. So these are going to be the units in my denominator underneath our radical here. So meters cubed per second squared. So I need to erase this here. What I want to do at this point is go ahead and record this value because we're going to need this value again. And since you have already written the values down, you've put forth the effort to calculate the value. Right here, there's no need to do that again. So let's go ahead and record that value. I'm just going to put a star. We're going to make a note here. I'm going to say the product of the universal gravitational constant and the mass of the sun is equal to 1.32733 times 10 to the 20th meters cubed per second squared. Okay? All right, let's continue on. Orbital time period of our unknown planet is equal to 2 pi times the square root. So we need to do the division under the radical here. And this is going to give me 3.5471 times 10 to the 15th. And let's take a look at our units here. So we're dividing fractions here. What we have is meters cubed, and algebraically we know that that is meters cubed over 1. We're dividing this by meters cubed per second squared. And what we need to think about is the old algebra rule that says whenever we divide fractions, it's like multiplying by the reciprocal of the denominator. So this is going to give us meters cubed over 1 times the reciprocal of the denominator here is going to be seconds squared per meters cubed. As you can see, our meters cubed will cancel, leaving us with units of seconds squared. Okay? So we performed our unit cancellation here. So under our radical, we have our numerical value and our final unit value here. Now what we need to do next is go ahead and take the square root of not only the numerical value, but remember we have to take the square root of the unit value too. So let's go ahead and do that. So I have orbital time period of our unknown planet is equal to 2 pi times okay, so we've taken the square root of the numerical value. Now we need to take the square root of the unit value. The square root of seconds squared is seconds. Okay, and this is going to be 59,563,466.14 seconds. Okay, let's multiply this value by 2 pi. Okay, and right now, our orbital time period, this is going to be our calculated value for part A. Now in part A, we have to quote our orbital time period in seconds, days, and years. And in seconds, we have 374,248,295.3 seconds. Okay, and so I'm going to write our answer right over here. Okay, we need to perform dimensional analysis. We're going to convert this value that's in units of seconds to units in days. So we're going to multiply by a ratio that's going to eliminate our units of seconds, and we know that in 1 hour we have 3,600 seconds. So as you can see, our units of seconds will cancel. We're left with units of hours, but we need to perform one more step. We know that in 1 day we have 24 hours. You can see we have hours in the numerator and hours in the denominator. So our units of hours will cancel, leaving us with units of days. So let's go ahead and multiply through here. And I get 4,331.57 days. Okay, so I'm going to transfer that answer over here. And we have one more step. We need to convert this from units of days to units of years. So we're going to perform some more dimensional analysis. We know that there are 365.25 days in 1 year. As you can see, our units of days will cancel. And so we're dividing this value by 365.25. And that's going to give us 11.859 years. And I'm going to write this value over here. Okay? All right, so that takes care of part A. Now we need to take care of part B, calculating the average orbital velocity of our unknown planet. So I'm going to go ahead and erase the work that we've done so far. Okay, I'm going to use the base equation for average orbital velocity, which is equal to the square root of the product of the universal gravitational constant and the mass of the sun divided by the average orbital radius of our unknown planet. Okay, we can just fill in some values here. Now, from part A, you've already calculated the product of the universal gravitational constant and the mass of the sun. Remember, we made a note over here. So what I want to do is plug this value into the numerator underneath our radical. So I have 1.32733 times 10 to the 20th meters cubed per second squared. And then we're going to divide by the average orbital radius of the unknown planet. And we calculated, we did some dimensional analysis over here. Remember, we converted from units of kilometers to units of meters. I have 7.78 times 10 to the 11th meters. Okay, so let's take out our calculator. Let's go ahead and take care of the numerical value here. What we have is average orbital velocity of our unknown planet is the square root of 170,607,969.2. Now let's talk about our unit value. So in my numerator, I have meters cubed per second squared. We're dividing this by meters, and we know algebraically we can write this as meters over 1. Remember, dividing fractions is like multiplying by the reciprocal of the denominator. So I've got meters cubed per second squared times 1 over meters. So one of my meters is going to cancel. This will leave me with meters squared per second squared. So that's going to be the units under the radical there. Now we can simply take the square root of both the numerical value and the unit value. And this is going to give me 13,061.7. That's the square root of the numerical value. The square root of the unit value is going to be meters per second. Okay? So this is the answer for part B. I'm going to write the answer over here. 13,061.7 meters per second. Okay? In part C, the problem asks us to identify the unknown planet, and we need to take a look at page 915. So let's go ahead and open our textbooks. We're going to take a look at page 915. On page 915, we have a row that says the orbital period in Earth days, and orbital period in Earth days is 4,331.57. So we're going to look 4,331. I've got Jupiter. So the unknown planet is Jupiter. All right. So now in part D, it wants us to identify the average orbital radius in units of astronomical units. So remember that 1 astronomical unit represents the average orbital radius of Earth. So the distance between the center of Earth and the center of Sun is known as 1 astronomical unit. And we know that 1 astronomical unit is equal to 1.5 times 10 to the 11th meters, okay? We know that the average orbital radius of our unknown planet is right here, 7.78 times 10 to the 11th meters. So what we can do is perform some more dimensional analysis. We're going to cancel units of meters, so we wind up with units of astronomical units. So I have average orbital radius of our planet, which we now know is Jupiter. This is 7.78 times 10 to the 11th meters. We're going to multiply this by a ratio that eliminates the units of meters. So this is going to be 1 astronomical unit divided by 1.5 times 10 to the 11th meters. My units of meters cancel out. And so now what we can do is take a shortcut here. So we have 7.78 times 10 to the 11th and 1.5 times 10 to the 11th. So it's in scientific notation, and they're both times 10 to the 11th. They have the same exponent here. So times 10, those go ahead and cancel out. So I've got 7.78 divided by 1.5. This is going to give me 5.186 astronomical units. So what we can do is say that the average orbital radius of Jupiter is 5.186 times what Earth's average orbital radius is. So in part D, average orbital radius of Jupiter is 5.186 AU. Okay? All right, in part E, it wants us to calculate the force of gravitational attraction between the sun and our unknown planet. And it tells us that we need to take a look at page 173. That's where the mass of the planets are listed. So I'm going to free up some room here. So the mass of Jupiter Let's take a look at page 173. It tells us that Jupiter's mass is 1.90 times 10 to the 27th kilograms. And we're going to need this value to calculate the force of gravitational attraction between the Sun and Jupiter. We're going to use the equation, the universal law of gravitation. So force of gravitational attraction is equal to the universal gravitational constant times the mass of the Sun times the mass of Jupiter, divided by the center to center distance. And this has to be in units of meters, okay? So here we have 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. We're going to multiply this by the mass of the Sun, which is 1.99 times 10 to the 30th kilograms. And then multiply that by the mass of Jupiter, and we just looked that value up, 1.90 times 10 to the 27th kilograms, divided by, here we performed the dimensional analysis earlier, 7.78 times 10 to the 11th meters, and we're going to square that value, okay? So, we already know the product of the universal gravitational constant and the mass of the Sun. We made a note of that earlier in the problem. So let's punch that into our calculator and multiply it by the mass of Jupiter. Okay? And in my numerator, this is going to give me 2.52193 times 10 to the 47th. And what we're going to have is Newton meters squared in the numerator. We're dividing this, and we have to square our center to center distance. This is going to give me 6.05284 times 10 to the 23rd. And not only do we have to square the numerical value, we're squaring the unit value. So I have units of meters squared. So just taking a look at the units right here, I've got Newton meters squared per meter squared. You can see that units of meters squared are going to cancel. And then we know we're in a good spot here because the units of force in the metric system are in units of newtons. So we're looking good here. So let's go ahead and divide. And the force of gravitational attraction between the Sun and Jupiter is equal to 4.16652 times 10 to the 23rd newtons. Okay, and that is part E. There is the answer to part E. So, a lot of newtons. So I hope this problem has helped you today. If you have any questions, you can send me an email or a message through Canvas. Or as always, you can contact me by phone. I hope you have a great day.